Once the design phase has been completed, the runtime phase can start. It targets the monitoring of functional and non-functional properties during the execution. In particular, it involves the interaction between the system of systems, that is the controlled environment, and a new component or device, that is the system under auditing. In this demo, we will focus on setup and execution of one of the runtime phase components, that is the auditing framework. In particular, we will show the join interaction between its three main components that are the ontology manager, the monitoring engine, and the predictive simulation. The auditing activity starts with the selection of the auditing framework setup, that includes as first step, the pre-setup phase. During this step, Bieco provides the user the possibility to explore the classification and categorization of the different systems of systems, their devices and components. Indeed, through the interface, a list of different systems of systems is shown and the user can select the most suitable one. In this case, the autonomous navigation. Then, the list of relative devices is visualized, so that the user could select the target of the auditing stage. In this case, Robot Unit 1. Successively, the list of the components of the selected device is provided, so that the user can select the suitable one. In this case, Local Planner 1. At this point, the specific component skills are visualized: connectivity and movement. The user decides to select connectivity, because it is considered the most critical from the security point of view. The lists of the most suitable functional and non-functional properties are then selected and visualized. These are presented as high-level specifications and called abstract rules. They are divided into two groups: standard and pure predictive. The standard rules are non-functional properties that can be assessed through monitor. For instance, the user can select the maximum number of established simultaneous connections. It targets the mutual interaction between the Local Planner 1 and the autonomous navigation, that is the controlled environment. In this case, rule boundaries can be established, either using data collected during design time phase, or provided by the user. They remain valid for all runtime execution. The pure predictive rules are instead functional properties that can be predicted through digital twin. For instance, the expected communication pattern through an ordered list of message types. It focuses on the specific behavior of the Local Planner 1 and requires that the digital twin predicts and forecasts to monitor the specific messages order. If not available already, as a final step, the user needs to insert the boundaries for the selected abstract rules. In this case, the maximum number is set to 1. This concludes the pre-setup phase. Then, a set of useful downloadable artifacts is proposed to the user. These include a set of guidelines for using the DSL language and derive the digital twin, a jar of the executable probe, and a set of guidelines useful for instrumenting the code. At this point, the control goes back to the Bieco GUI. At this stage, the user works offline for preparing the required digital twin and instrumenting the Local Planner 1 and the controlled environment and the digital twin itself with suitable probes. In this short video, the probe inserted into Local Planner 1 is visualized. The development of the models for the digital twins is guided by a domain-specific language, also known as DSL. The DSL is based on a grammar that contains rules that guide the development process at the user side. These rules specify the way in which the models shall be structured. For example, the grammar rule for entity enables definition of structures for holding behavior specification. With the support of the Xtext framework, when code is written according to the imposed pattern, corresponding source code is being generated. In practice, the user, who is also the developer of a software component to be integrated in a supply chain, uses the domain-specific language to specify the behavior of this component. This implies that with every new software component that is introduced in a supply chain, corresponding executable models need to be provided as well. When fed with real-time data, these models become digital twins. For creating the executable models, in a Java development environment that integrates Xtext, the user creates within a project a file with the extension that refers to the language. Automatically, the pop-out menu enables usage of pre-defined structure, like package entities. The user then starts to write the behavior by structuring it accordingly. In the running example, we define the behavior of the local planner that guides the navigation of the robot. With every build, the code for the executable models is generated. In the running example, the navigation module interacts with other entities. This interaction needs to be specified in the behavioral description. Interactions are captured in dedicated constructs that enable gathering information that is being exchanged. This information is later on encapsulated within specific events that are monitored for conformity with the execution in the real-world or controlled environment. Decision events will be those events that cross the architectural boundaries of an internal component, whereas normal events describe normal input-output interaction with components within the same architectural structure. Fast forward, all behavior is being declared and corresponding models are created. These models are then packed as jars and executed in a predictive simulation environment. Now, the auditing framework setup needs to be completed with the last step, that is the finish pre-setup. In this case, the user first needs to upload the prepared digital twin. Then, the user needs to finalize the well-defined rule by providing the identifiers of the probes injected. In this case, for the rule named maximum number of established simultaneous connections, the user inserts SUA probe. For the pure predictive rule named expected communication pattern through an ordered list of message types, the user inserts DT probe. Here we see the controlled environment for this demonstration. It consists in a Capella simulation, representing the multi-robot navigation scenario for intralogistics, as depicted in the overlay. The system under audit is part of the robot on the left, with probes being injected into the local planner component for the navigation. Under normal conditions, both robots should follow the computed path, while avoiding environmental objects and each other. With the button Start Auditing Framework, a start command is sent by the orchestrator to the auditing framework, so that the auditing framework can start. Monitoring engine goes from online state to running. It raises up the complex event processor and receives the rules defined in the setup phase. Then, it compiles the rules into meta rules and instantiated rules. At this point, the monitoring starts listening to the events sent by the probes on a dedicated channel. Here is shown the SUA probe injected in the local planner 1 that sends events related to velocity and score. In parallel, listening from the same channel, the predictive simulation receives the events useful for fed abstract models. These are executed at a faster rate than the controlled environment, and can therefore provide predictions about trusted behavior. Considering the rule called expected communication pattern through an ordered list of message types, here we show the DT probe injected into the digital twin. It includes DT forecast event, containing a digital twin prediction in terms of a sequence of velocity and score events. Using the data of the DT forecast event, the monitor instantiates the meta rule into a new rule and injects it into the complex event processor. The time frame validity of the new rule will be set to 5 seconds, as established in the DT forecast event. On the monitoring side, the monitor continuously receives the SUA probe events, containing score, velocity and connection status, and checks the set of instantiated rules. For the sake of this demo, a malicious code attack has been simulated. For this purpose, the malicious code injection is performed through the UI provided with the controlled environment. Due to this, the number of connections between the local planner, 1, and the global planner increases, as shown in the UI. On the monitoring side, this causes the violation of the maximum number of established simultaneous connections rule, as shown in this video. In this case, a notification is sent to the Bieco platform, and the auditing framework stops immediately. Once this untrusted behavior is detected by Bieco's auditing framework, the dynamic configuration of the system under test can be triggered. Here this is once again simulated via the controlled environment UI, returning the system into a safe and trusted condition.